And following his PhD, he moved to Cambridge in the UK, where he was first a junior research fellow at Peterhouse College, and later an assistant professor at the Department of Mathematical Sciences. And now, Julian's research interests are extremely broad, I would say. He works not only in combinatorics, but also in analysis, geometry, and probability theory. And he's been responsible, or partly responsible, for many recent breakthroughs in Ramsey theory, and this will be the topic of the talk, but also in the study of random matrices, random polynomials, and sphere packings. His work has been awarded by several prestigious awards: the 2021 European Prize in Combinatorics, the 2023 Salem Prize, and the 2024 Whitehead Prize. And without further ado, let me hand it over to Julian.
Great, thank you. Okay, thank you very much, guys. So this will be a course on Ramsey theory on graphs. And because it's a short course, so I'm also going to take a very narrow sliver of that topic. But let's just say, if you don't know anything, the topic is you have essentially usually a complete graph. You give it to someone to color with two colors, the edges, and we're interested in what structure is in this two coloring. Okay, and I'll say more specifically about what we mean, but let me just get a list of topics here on the board of what I plan to do in this class. So I think the difficulty level of this class is going to look something like this. So those are just the axes. It's going to, but actually, no. I was going to do it in red, obviously. But the beginning will be sort of gentle, and then it will kind of increase toward the end. Okay. Good. So in the beginning, okay, right. Sorry. So I'm going to talk, and I'll put it here. The whole course will be focused on essentially the Ramsey numbers R3K. So this is partly just to show, even if you take this one sequence of numbers, we already get all kinds of rich combinatorics out of it. And really, people have been thinking about this stupid sequence for decades. And as we'll see, and I won't even be able to say everything that I can about this sequence, but there'll be a lot of interest here. Okay, so this will be broadly the topic. But let me sort of break down the lectures, or what I hope to do. Sorry, I should also say, this is really for the graduate students, and I am your faithful servant. So if I'm going too fast, don't jump in. There's too many researchers here that know essentially half of what I'm going to say. So it's not for them, it's for you, the graduate students. So please, please jump in, ask questions, say if I'm going too slow, if I'm going too fast. Okay, so the beginning, I'm going to start fairly slow. I'm going to, of course, define the Ramsey numbers, say the most basic things about them. And we'll start by proving a first lower bound on these Ramsey numbers. We'll also prove a first upper bound as well, just using some basic methods in probabilistic combinatorics. Then we'll push a little bit further, way deeper. Hopefully this is kind of where we'll end roughly today. Say something of this form. Then we'll talk about upper bounds for the Ramsey numbers. So interestingly, this is a nice moment. Actually, there's several moments of contact with Will Perkins' lectures, because he'll be talking about triangle-free graphs drawn from a uniform distribution. I'll be later talking about drawn like sort of in a green nibble, creating a triangle-free graph. But also there's another point of contact with the upper bounds for R3K. So there's a natural method using the hardcore model, as we saw today, to prove an upper bound. So I think Will give that proof, and I'll give us the semi-random method to give for upper bounds here. Okay, so so lower bounds, upper bounds, and then so there's no lecture on Wednesday, but Thursday, Friday, I'm hoping to talk about basically the result of Kim, who showed that R3k is at least k squared over log k. And while you might feel sad that this is only a log improvement over what I'll do essentially today or today and the beginning of tomorrow, there's actually a lot of really important and interesting ideas going into this result here. So it'll be sort of, I really try to give a good sketch or maybe even complete proof of Kim's breakthrough result on the 90s to prove this. And this matches the upper bound up to a constant factor given by R3k. Oh, I should also say that Matt Jensen on Thursday will talk about, on Friday, thank you, we'll talk about some progress on determining the constant here in the upper bound. Sorry, the lower bound. Good, okay, so I'm gonna, probably there's no questions. Oh, I forgot to say, Gabrielle is the TA for the course. Maybe just stand up or something. You can't see anything in this room. Yeah. Whoa, yeah, okay. So, yeah, so we'll have lots of nice problems. Please do use him as a resource. I'm also happy to talk to you. Grab me in the halls or whatever. Okay, so let's start at the beginning. Oh, sorry, are there any questions? And really do ask questions. Okay, everyone in the front row will ask one question over the all the Brazilians in the front row here. Okay, you better ask. Okay, so let's start at the beginning. And this part is meant to bore experts all in the back. So back to your laptops. Oh, I should probably define the Ramsey numbers. Okay, so R of k, I guess I defined it the other day, is the minimum n such that every red, blue coloring of the edges of the complete graph on 1 up to n contains a monochromatic case of k. Okay. So here I'm actually following a convention that I'm going to use throughout the class. When I say a graph, I will almost always mean a set of edges. This is a slight abuse of maybe what's standard, but it will almost always be a set of edges. Okay. Good. And the off-diagonal Ramsey numbers, which you probably already know the definition of, is the same as the above, but now I'm looking for, given a red-blue coloring of this, I'm looking either for a blue case of L or a red case of K. So this is the minimum n such that every red, blue coloring, and I'm remembering to write large, I hope. Please complain if you can't read it. Contains, I'll just go here, either a red case of K or a blue case of L. Okay, so just to remind ourselves what planet we're on. So Rk of k, of course, is just equal to R of k. And R3k, which will be our interest of object here, is I'm looking either for a red, what did I say, blue? A blue triangle, or a red complete graph. Okay? But we're essentially going to forget about colors from now on. What are we interested in? We're interested in, we could just think about the blue color. And what is this? I'm trying to find a large triangle-free graph that has independence number, so the complement is no clique, independence number at most k. Does anyone not know what independence number is? Maybe people don't raise their hand if they don't know things. It is charming, though. Okay, thank you very much. Okay, I'll quickly define it. So let G be a graph. And I'm writing very, very large. Wow, okay. The independent, sorry, let's just say it like this. So a subset of the vertex set is independent if there's no edges in it. So it induces no edges. So if I induces no edges, what's the picture? This is I. This is independent if there's no such pair like this. So this is not allowed. So no connections. And the independence number is simply the size of the largest independent set. And I'm going to use throughout this course alpha of g to denote this number. So this is the max I such that I is independent in G. Great. This is the independence number. Great. OK. OK, but before we start really delving into these quantitative questions that I had up on the board here, let's just get a first grounding. What can we say about these numbers just from the beginning? So first of all, it's not completely obvious that they exist even. And this was proved by Ramsey about 1 million years ago. And we'll do the first sort of effective upper bound due to Erdős and Szekéresi right now. OK, so this is theorem. Erdős and Szekéresi. Perhaps we already saw this in Rob's lecture the other day, which is from ancient times, but actually a very useful point of reference for us. So RLK is at most k plus L minus 2, so this binomial. OK, so the proof is quite simple nowadays. Well, OK, so what I'd like to do is prove this by induction. And the first thing to know is that if L or K is 2, then it's trivial. So R of 2K, OK, of course, this is equal to the same thing when I flip it by symmetry. Whoops, 2. Whoa, 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 whoa. Let's just say that. Is equal to L. OK? Because if I have, just so this is a sanity check to make sure of the definition, how big can my n be so that I have no k sub L in one color or k sub 2 in the other color? A k sub 2 is just an edge. So I'm not allowed to use that color at all. So how big does n have to be before it's a KL? So just L. Great. So this is my induction step. And now I'm going to prove the following recurrence. So RKL is at most R of K minus 1 plus R of, for some reason I've reversed everything today. OK, it didn't matter, of course, but it will confuse me later. OK, maybe not. OK, LK minus 1. OK, so let's prove this recurrence. And we'll see once we have this recurrence, we're done. I guess I should have said for L and K bigger than 2 strictly here, if I was being very careful. OK, maybe let's be careful. OK, so what do we need to do in order to prove this? What I would like to do is take a graph on this many vertices, this plus this many vertices. So set n equal to blah, blah, blah. OK, and now I need to show that no matter what coloring you give me, I can find either a k sub L in blue, a k sub R in L. OK, so here we go. And I'm going to, of course, use induction. So you give me a coloring of this k sub n. OK. Any old coloring of the edges. And now what I'm going to do is just take some vertex pick some vertex in this graph here. In fact, any vertex will do. OK, this vertex will be joined to some things in red in the rest of the world. And it will be joined to some things, if I can find the color, blue. Here we go. OK, if this bit of the world here is bigger than R L k minus 1, sorry, bigger than or equal to R L k minus 1, what does this mean? Either I can find a complete k sub L in blue here, in which case I'm done, right? Or I can find a red k sub k minus 1, which I'm almost done. I just need one more vertex for that clique. Oh, we'll just add that vertex, and that's my clique. OK, so either I'm done, or this is smaller than this. OK, now let's look in the other color. By the same argument, I can say that this bit here has size at most R L minus 1 times k minus 1. Right? Otherwise, I find a red k sub k, I'm done. Otherwise, I find a blue k sub L minus 1 in here. And then I extend it by adding that thing in blue. OK? But now, how many vertices are here? Audience participation here. Let's go. Who doesn't know? Who's not a grad student here? not a researcher. You guys know already. Phew. So how many? Maybe this is not allowed, but OK. How many vertices in the bottom? Downstairs. Sorry?
You add them up.
So what's the contradiction? Sorry, all I'm looking for here is that the number of vertices down here, well, the whole graph has size n. This has size n minus 1. But I told you n minus 1 is this plus this. But on the other hand, I said it's this plus this minus 2. So this is a contradiction. I'll just write it on the board, because we're just getting used to things right now. So this is R. So n minus 1 is at most R L minus 1k plus R L k minus 1 minus 2. But this is contradiction. Contradicts the choice of n, so I proved this recurrence. OK, so I'm not quite done. I've just proved this recurrence. I want to get this bound. But now I just noticed that these binomial coefficients satisfy this recurrence by using whatever Pascal's identity or whatever it's called. So we have, I can't believe I'm actually writing this on the board here. OK, here we go. And possibly correctly, yes. So just use this recurrence, then done. OK. OK, so this gives us some sort of, I lost the thing. Who saw where it went? This is something else. Oh, no, it's not. Sorry. This is not what I was using before. OK, so this gives us some sort of anchoring of what the bounds could be. Let's note a first corollary of this. OK, so the diagonal Ramsey numbers are cool, natural object. What do they say about the diagonal? That R of k is at most. OK, there's going to be like some minus 1s here, but it's basically 2 to the k, choose k. I guess there's minus 2, minus 1. But not going to make a lot of a difference. OK, how big is this thing? Right, this thing is basically 4 to the k divided by square root k times some constant. OK? I mean, I should say this is really approximately Oh, by the way, how do you prove this? It's useful, and we'll use it elsewhere, so I'll just quickly say it, is you'll just use the Stirling formula, right? So how big is this? If someone asks you on the street, how big is k factorial, right? You say k to the k. And if they really want to know what it is, you say, fine, fine, fine. There's an extra e to the minus k. Fine. And if they're incredibly impolite and demand to know what the answer is, there's an extra square root constant, which I actually don't know off the top of my head. I think it's this. And that's really up to lower order terms. Sorry. What is it? Right. OK, that will actually come in handy in a second. OK, we care also about the off-diagonal Ramsey numbers, R3k. What does it say there? R3k is basically k squared, is at most k squared. It turns out this is actually not so far from the truth. But there's a lot more to say. OK, but of course, these are all upper bounds. If someone is just telling you upper bounds, they can be cheating. Like, what's happening on the other side? We need some sort of comparable lower bound to sort of understand what's going on. So I'd like to start by and this is really the end of our discussion of the diagonal Ramsey number. I'd like to think a little bit about the lower bound for the diagonal Ramsey numbers. OK, so a first lower bound that you might think of, and in a sense, to say it these days is a little bit silly, but I really do want to say it, is there's a natural lower bound of like k squared. So what's the construction here? You take k minus 1 blobs here and color each one of these blobs inside completely red. Sorry, and these blobs have size at most k minus 1. And color everything between the blobs blue. Right, so now you can't have a red k sub k because it would have to fit into all one blob, not possible. Can't have a blue k sub k because they'd have to be in all different blobs, not possible. So this really gives a lower bound. I found a graph that has no k sub k, and it has k minus 1 squared vertices. In fact, there's technically a plus 1 because it's the smallest for which it does hold. So, yeah. And back in the Stone Age, people really thought that perhaps maybe something like this is more closer to the truth, right? Because what do we have? We have this very sort of naive inductive argument. Like, we didn't do anything with the coloring. We just take a vertex, look inside, giving this exponential bound. And on the other hand, we have this very natural coloring that naturally forbids these k sub k's. You might think that's closer to the truth than that. So it was really a surprise when Erdős came along with one of the first examples of the probabilistic method and showed, actually, it's more something like this. It has exponential growth. So let's warm up by proving this. I just keep picking up chalk and then not putting it down. Also, what happened to the other eraser? Ah, it's here. My goodness. OK, so theorem. This is due to Erdős, and was really one of the first, not the first, but one of the first sort of influential applications of the probabilistic method in combinatorics. And it's 47. OK. So R of k is at least 1 plus, 1 minus little o 1 times k over root 2. OK, so this actually gives me a moment to remark on asymptotic notation, which I will use a lot of. This little o1 here, this means a quantity that tends to 0 as, OK, it's not completely clear, but here there's only one parameter, so as k tends to infinity. So this is little o1 means goes to 0 as k tends to infinity. I could be explicit and write little o k tends to infinity if I want to be. Okay. if I want to do this. OK, let's prove it. It takes only 2 lines. And I think it's a good warm-up for the kind of argument that we'll have in this course. Great. OK, so the idea is something we'll see a lot of in this course, and I hinted at with the probabilistic, saying it's probabilistic method. Don't try to construct a stupid coloring like this, right? Just choose one at random. So let n equal this number. I don't want to write it again. OK, whatever. OK, if this is confusing and annoying, just think of this as minus delta for now, for some fixed delta. Also, here's another thing that you'll see a lot of in this course. You might complain that this might not be an integer, right? Who's bothered by that? Who's bothered by that? No. OK, usually there's some. Just kidding. OK, so we're not going to be bothered by that in this course. OK, so let chi be a random coloring of the edges. Oh, right, I'm writing big. Of the complete graph on this many vertices. And now I'm just going to calculate the probability that there exists a monochromatic clique of size k. So here we go. So the probability there exists a mono k sub k in this coloring is the following. So I'm just going to show that this is less than 1, and then I'll be done, because there must exist some coloring that satisfied this. OK, so this is a big confusing union here, right? It's the union of every possible k sub k saying I'm either I'm monochromatic or not. So this is the union of, for all, maybe I'll call it I, in n choose k. So this means all the k sets. Probably IMRA used this notation. All the k sets of 1 up to n. So I, all the pairs are mono. Now just apply the union bound to this thing. Oops. How many such sets are there? There's n choose k. So I'm summing over all such sets. What's the probability that a fixed set is monochromatic? Well, it could either be monochromatic red or monochromatic blue. So there's 2 choices there. And now all k choose 2 edges have to come up the same. So that's 2 times 1/2 times k choose 2. OK? And this is basically the end of the proof. I just have to convince you that this is less than 1 for this choice of n, which is just some nerdy math. So, oh yeah, actually this is a good moment. This is an inequality that I'll use about 1 million times in this class. N choose k is at most En over k to the k. This is always true for all such k. OK, and what's happening here? This little 2 doesn't really matter too much. This is 2 k choose 2 minus, sorry. OK, I'm running big, but it's running out of space. So let's factor out a nice k from everything. So this is En over k minus k minus 1 over 2 to the k. OK? And now we have to remember what our choice of n is. So n is roughly 2 to the k over 2. So that's balancing with there's a stupid 1 here, but don't worry, but that's basically balancing with this. That's giving that root 2 downstairs. And then you have to be a little bit more careful so that this k, sorry, so then there's n, there's the k which cancels with this k, there's the e that cancels with this e, and that extra root 2 is canceling with this extra root 2 here. So this is less than 1. Okay. For a sufficiently large n. And this is the proof. Good. OK, so basically, what do we know? I wrote all this little bit here for a comment in 1 minute, but basically the Ramsey number is at most 4 to the k, and at least 2 to the k over 2. The reason I wrote this is because, interestingly, this is almost the state of the art on the lower bound. So this was in 47. All that's happened since 47 is this root 2 has moved into the, into the numerator here. So it's this, and not for lack of trying. So this is really amazing that any kind of motion on this lower bound seems to be a really interesting problem, perhaps for an ambitious graduate student out there. No, that's not a joke. Okay, so that's all I want to say about, actually, I want to look at the time. Are there any questions, actually, at this point? While I look at the time. So this is actually all I want to say about the diagonal. I got us kind of used to the Ramsey number. Now let's get back onto the off diagonal. So what about some lower bound for R3K? Okay, so we had this k squared upper bound. I just want something non-trivial. Okay, so we might be inspired by our use of randomness here. Randomness seemed to be very good at getting into all of these independent sets and ruining them. But the problem is, if I take a random coloring, I'm going to have tons of triangles, right? It's quite likely to have a triangle. So if, say, p is 1/2, I'll have 1/8 will be, or 1/4 will be monochromatic triangles. So that's way, way too many. Okay, well then you say, well, wait a second, this is unbalanced. Then it makes sense to have the colors of different sizes. Okay, so it's a good idea to sample from G and P, where P is not 1/2. Okay. So I was going to define G and P here just very quickly. Probably lots of people will shake their heads. So, all right, G and P is a probability space where each graph, on each graph, on graphs on, I'll always fix the vertex set to be 1 up to n. And each edge is included with probability p. Okay? And just a notation, I'll often write G tilde G and P just to mean a random sample from this space. Okay, so now what we'd like to think is about is well, what p do we, what's the initial p for which we have a triangle? And unfortunately, this density is very, very low. So it's actually a bad idea. But what we can do is do a slight modification of this idea. And this comes from another ancient paper of Erdős, so I think this is from the 60s. And gives the following lower bound. So k over log k to the 3 over 2 for some. I'm not going to worry too much about what the constants are. I'll just say for some constant c. So this is a nice first bound. What's the proof? In a word or a sentence, first I'm going to sample G and P at an appropriate density. There's going to be triangles at that density. But now I'll just delete vertices from every triangle. I will only decrease the size of the largest independent set, right, because I'm only making the graph smaller. And in this deletion, I'll remove all the triangles. Okay, so let's quickly do it. So I'm really doing this because it's sort of the zeroth idea here. And everything beyond this will really require some sort of really genuine idea. Good. OK. But before I get there, I need to say a couple things just about G and P. Just the most basic things. We'll do it quickly. But we'll get there. Are there any questions at this point, actually? This is maybe a good point. OK, so So by the way, so I want this lower bound on R3K. This will be common. So really, it's better to think of it as I want to construct a graph on n vertices that's triangle-free. It has some bound on the independence number. So let me just write it down specifically for this. So we will construct a graph which is on n vertices, which is K3 free, and has independence number. So this is kind of the important thing, n to the 2/3 times log n. Here there'll be some constant. OK, if I can construct this for all sufficiently large n, then I'll have proved this, right? Because what I can do is take k equal to the independence number here, and now I have this bound. Right, so this graph will be my blue color. I have this bound. Now I just solve for n. So this is k over log n to the 3/2 is equal to n. Notice here that there's a log n here, but log n and log k, they're going to be just a polynomial apart, right? Because the independence number is at most k. It's going to be at least like square root k. So I can just replace n with k here at the loss of some constant. But I don't care about that. Sorry, I should have had the right bound here. Don't worry about that anyway. Sorry, maybe I'll do this. Right, so I've constructed a graph on this many vertices with no k sub k, I guess plus 1 or whatever. So this is a lower bound for the Ramsey number, R3K. So I'll sort of work in this inverted form. Oh, and by the way, we only need to do it for sufficiently large values of k. You might say, oh, like, we'll assume n is always large. That's fine, because if it's not, I can just, if it fails for some finite number of values, I can always just adjust this constant downward a little bit. In any case, we really care about the asymptotics, but in case you were, any questions about that? OK, so it's pretty clear I'm interested in the independence number. What's the independence number of the random graph? I'll just say one quick fact about this. So if p is less than 1 over n, is at least, and this here I'll mean greater than means this is growing asymptotically faster than this. So in this case, p times n is tending to infinity. So for every constant I can put here, it's bigger. OK, it doesn't really matter. I'll just put it most to half. We'll certainly won't be interested in graphs that dense anyway. So let p be growing like this. And now sample g from g and p. What can I say about the independence number? Alpha of g is at most 2 plus little o1 times log pn over p. Okay. One quick remark is that this is actually also an equality. It's more challenging to prove the equality, and I'll only need the upper bound here. OK, and the proof is quite simple. I'm just going to do a union bound over all sets of the appropriate size. Okay? So let k be this number here. OK. and now, just as in the proof of Ramsey, I'm basically union bounding over all potential independent sets. So the probability there exists in I such that I in such that I is independent. Okay. Now there's no space, so I move here. Okay, so this business is at most the sum over all possible sets. So again, let's just be and choose k times, okay, now I fix some set. What's the probability that that given set is independent? So still there's k choose 2 edges that all have to come up the same. But now the probability is 1 minus p. So it's k choose 2. And just we estimate just as before. So this is En over k, my favorite inequality. And my second favorite inequality, this course, will be e to the minus. Okay, so also used approximately 1 million times will be this inequality. When I guess x is, I think it's even x is at most -1, but almost always we'll have it like this. Okay, so this is same as before. And now I just check that my choice worked, right? So now I have to remember what, okay, again, this business is just irrelevant. This 1/2 is irrelevant because it's multiplied by p. What is k? Well, k is 2. Well, that's going to cancel with that 2 in the exponent. The p here is going to cancel with this p in the exponent. So this is going to be like log pn in the exponent, minus log pn. So that's like 1 over pn. So just using the definition, 1 over pn, so this is k. The n's cancel, p times k. And now this business here, what's p times k? Just going back to here, this is like log pn. So this is e over 2. This doesn't really matter, but log pn to the k. Good. And now I said that p times n is tending to infinity. So this business is tending to infinity. So this whole business is tending to 0. Okay, raising it to a k just is stomping on it more. Okay, so that's it. Okay, good. Okay, so the second fact, so I'm going a little bit slowly, really this putting one fact at a time. So if you find yourself falling asleep, that's fine. Sleep is also important. Okay, so here's another fact. Okay, so this talks just about independence number. I need to say something about triangles. And the thing is just what you expect. Okay, so we go very quickly. So p, again, if you're bigger than 1 over n, and I'll just bound myself, whatever. It's not super important. I could say something much stronger. Again, let G be distributed as G and P. Then the number of triangles. Sorry, I forgot to write a very important thing here. This is with high probability. Right, so meaning the failure of this tends to 0. So the probability, the independence number is bigger than that, tends to 0. Okay, so how many triangles are in this graph? The answer is it's concentrated around the expected number of triangles with high probability. So p cubed times n choose 3. Okay, so you sample this random graph. You really know how many triangles it has. You really know the independence number. And then we're going to put these two ingredients together. so proof. So let's see. I think I might just prove the upper bound, which is the easier bit. And I'll just say how to do the lower bound, and maybe that's a good first exercise. So proof. So I just want to prove the upper bound. So proof of upper bound. Maybe I'll write this to make clear. OK, so it's, again, a very easy exercise. So if you know what to do, let x be the random variable that counts the number of triangles in G. OK. It's easy to calculate the expected number of such triangles. Right, so I can write this as a big sum of indicators over all potential triangles. How many potential triangles are there? There's n choose 3. Now fix one of those triangles. What's the probability that given triangle is in? It's p cubed. Each edge has to be included. And that's the expectation. OK. Oh, sorry, you need to prove the upper bound and lower bound together. OK, let's prove the whole thing. I was being silly, because I wrote 1 plus little 1 rather than, OK, something else. It's not so hard. OK, so I want to show that it's a good review anyway, if you don't do these things every day. So I have a random variable. I know its expectation. I just like to say that it's concentrated about this expectation. What's the very first 0th idea you have? I don't know, maybe somebody, front row. Second moment, right? So you just want to you want to calculate the variance, right? You say, so we use, I might as well get this on the board, the following inequality of Chebyshev, which is the very first concentration inequality you'll ever come across, is that the probability that you deviate from the mean by t is at most the variance of x over t squared. Right? So all I need to do, if you think about it for a second, is calculate this variance. By the way, what should the variance be? There should be a guess for what the variance is without calculating it all. Look, I have a bunch of these triangles in a big graph, right? They barely interact at all, right? You choose a random triangle, you choose another random triangle. So it basically looks like a sum of independent random variables, right? So if the probability of coming up heads is p for a sum of Bernoullis, right? The variance is p times 1 minus p. And the variance is sum for independent random variables, right? So what we expect is basically this same quantity, OK, times, sorry, let's say, expect that the variance of x is very close to p cubed. OK, this is not so important because it's going to 0 anyway, times the number of samples. And this is basically true. So how do we actually do this? We compute the variance. Maybe I'll just leave this for an exercise from here, right? So what is the variance? I can write this as the second moment. So this is expected value x squared minus the expectation. Now these are quantities I really can just put my hands on and compute. Okay. So maybe this is a good exercise. So exercise. Calculate the variance and use this Chebyshev's inequality here to finish the proof. Oh, by the way, I wrote this 1 plus little o1. Just again, let's just work in this back of the envelope way here. So if this is the variance, how do we expect x to typically be, right? We expect it to be typically not on the order of the variance, to deviate on the order of the variance, but the standard deviation. right? So we expect x is really typically its mean plus the standard deviation, which is a square root of this business here, plus, I'll just say big O square root of something that is completely illegible. Okay, square root of the same thing. And this big O I'm using a bit generally. So it's sort of varying at this scale. This is smaller than this, so this makes sense. Okay. So yeah, so the point of me saying this is not to bore you, but just to note that the distribution here is exactly what you expect from the Bernoulli case, at least as far as I care about here. So for IID Bernoullis. Okay, so I think I can maybe just finish this proof and then say something about the next. Yeah, perfect. Okay, so now I want to prove. Okay, so proof that, sorry, let's write it in this other form. So I want to show that R3K is at least K over log K to the 3 over 2. And what I'm going to do is build a graph G on n vertices that's triangle free. Maybe I'll stick with just K3 free. Triangle free and has independence number constant n to the 3 over 2 log n. Okay, so hopefully you're convinced by that is enough to imply that. Okay, so let's do this really quickly. Now that we have the tools, it's easy. Okay, so sample G from GMP, where P is equal to n to the minus 2/3. Okay. Now, we know that the, define. Sorry? Oh, sorry, thank you. Thank you. So now let G tilde be G, remove a vertex. Sorry, let me move it here. G is equal to G tilde minus a vertex from each triangle. Okay? Okay. Okay, so you might ask, how do you, which vertex do you choose? Doesn't matter. Just choose the lexicographically first, whatever. Okay. Yeah, so oh, sorry. Thank you. Yeah. I was so worried about writing big enough here. So yeah, G tilde, sorry, thank you. You take G, remove a, okay, independence number of G tilde, that's easy. It's obviously, quote unquote, obviously at most the size of G. All I've done is delete vertices, so independent sets only shrink. Now, that's a thing I know what the answer is with high probability. That's this log 1 over P business. So this is n to the 2/3, which conveniently agrees with what I was claiming, log n. I'll just slap a big constant there, whatever. 3 was enough, but big old constant. So this is with high probability. And on the other hand, okay, so now I need to worry about what if I destroyed all the vertices in my graph G. So I need to check the size of my G tilde. It could a priori be empty, but we know it's not, because we know how many triangles there are. So I didn't delete too many vertices. So G tilde is always less than, this is just deterministically, less than n minus the number of triangles. But I know how many triangles there are with high probability. So this is at least n minus p cubed and choose 3. OK, so now fast math. Well, this is n to the 2/3. I raise it to the 3, so it deletes one of the n's. So there's an n remaining, and then there's a third. So this is n over 3 with high probability. And what have I done? I've created exactly the graph that I want. OK, with a 1/3 there, but you can just reparameterize, and I'm fine. OK. Any questions? There's no clock, eh? I have to always look. OK, perfect. I have 2 minutes to explain what comes next. OK, so this idea was like a little bit naive, right? What was I was doing is every time I see a triangle, I just delete one of these vertices. But these are Ramsey numbers. Like the vertices are the most precious resource I have. So it's a much better idea, perhaps, to delete. Every time I see a triangle, I delete an edge from it. But now you have to be careful, because you're removing edges, and the independence number might increase. OK, but assume that you could delete these edges in a random-like way, so that the resulting graph still looked like G and P, and we still had this kind of independence number. How far could we get? Well, we want the number of triangles, right, to be much smaller than the number of edges in my graph, right? So then intuitively, deleting these few triangles in some nice random-like way will not disrupt the density too much. So this could give you something like P is something like n to the 1/2, just solving that. And if I have this, well, I know what, assuming the graph still looks like a random graph, what should the independence number of this modified graph be? Well, then you expect the independence number to be like log n, OK, log pn, whatever, p, which would give n to the 1/2 log, something like log to the n 1/2, which would then give R3k is at least k over log k squared, right? Which matches the upper bound up to this power of log. OK, in the next course, in the next lecture, we'll show how to make this line of inequalities like rigorous. So we'll be able to show we really can delete so that we maintain this kind of behavior and then can conclude this. OK, thank you very much.